Astronomer Sten Odenwald explains how the night unfolds.
All the lights went out, quite literally. It only took about 90 seconds for fully operational to complete blackout conditions.
At dawn, the thermometer reads just 8 degrees, and the power's still out. Life or death work runs on emergency generators. The blackout lasts 12 hours. But the disaster could have been much worse. If not for a few transformers in the US, millions of Americans might have lost power too.
With only a couple of more components damaged, the entire East Coast would probably have gone down as well.
But what caused the transformers to overload so violently? Why did Quebec plunge into darkness? This wasn't a terrorist attack or human error. The culprit wasn't of the Earth. It was the result of a gigantic explosion 93 million miles away on the Sun. Three days before the power network collapses, astronomers at the Space Weather Prediction Center in Colorado monitor an active region on the Sun, when suddenly a giant explosion bursts from its surface. A white flash thousands of miles across and millions of degrees hot. 93 million miles later, a huge wave of radiation slams into Earth's atmosphere. Colored lights dance across the night sky from Alaska to Mexico. The solar storm that hit Quebec is the worst in living memory. But worse may strike the Earth in the future. And next time, we might not be so lucky. The Sun is capable of producing storms that could black out whole continents. North America would be crippled.
Losing the electric power grid, even temporarily over an entire continent, is a major disruption to the way we operate in the 21st century.
The Sun radiates more energy in 1 second than the world has used since time began. The byproduct of all this energy is vast amounts of magnetism. Huge magnetic fields loop across the surface. They bubble up from the core and punch hundreds of thousands of miles into the solar atmosphere before plunging back down again. These arcs are so vast, the Earth could fly through one with 100,000 miles to spare on each side. On planets like the Earth, every part makes a full revolution around its axis each day. But the Sun is a dynamic ball of gas. Its equator rotates in 25 days, but the poles take 35 days. The magnetic loops stretch and distort as it turns. Along each loop flow billions of tons of superheated plasma, electrically charged protons and electrons. A single loop contains the energy equivalent to 10 million volcanoes erupting at once. These loops are sometimes the first sign of an impending solar storm.
Currents, magnetic fields, the currents make forces, and if they add up in the right way, you can get very powerful forces that can cause these structures to blow up.
The smallest of the flares are more than 1 million nuclear bombs going off. The largest ones are 1 million times 1 million of these bombs going off.
Behind nearly all solar flares is a gigantic cloud of radiation. And in its sights, Earth. But its first victims are in outer space. These sparks are a visible sign of a clash hundreds of miles above the Earth's surface. A war between the Sun and the Earth's invisible defense shield, the magnetosphere. The magnetosphere completely envelops the entire planet. This invisible shield flows out from the Earth's core. It punches through the South Pole cocoons the entire Earth, then plunges back down through the North Pole. The more powerful the storm, the more dramatic the auroras. This high-altitude battle can cause problems for airliners. At the poles, the atmosphere is especially vulnerable to large bursts of radiation. The wave of energy causes havoc in the upper atmosphere, disrupting GPS systems and blacking out radio signals.
During intense storms, passenger aircraft have to divert to lower altitudes in order to regain communication with air traffic control.
On March 9, 1989, as the radiation from the flare arrives at Earth's upper atmosphere, the battle with the magnetosphere begins. But in Quebec, the power stays on. 4 days later, on March 13th, a second wave of radiation hits the Earth's atmosphere, and the aurora puts on an awesome show. As the northern lights dance in the sky, the lights in Quebec suddenly go out. How does a radiation cloud high in the atmosphere shut down an electricity network on Earth? To find out, NASA develops the OS-07 satellite. It can aim a battery of UV and X-ray telescopes at the sun. The mission will give scientists their first glimpse of a monster. This white spot might not look impressive, but it's the first image ever captured of the most powerful event in our solar system. It's called a coronal mass ejection, or CME. 10 billion tons of material explodes from the atmosphere of the sun. An enormous eruption.
There are magnetic turbulence and magnetic forces lower down in the solar atmosphere that cause literally the outer atmosphere to be blown out into space.
CMEs are an electrified tangle of charged particles and magnetic fields. A superheated bullet of matter from the sun. A CME looks like a solar flare, but it's 100 times more powerful.
Before we knew of CMEs, we thought that the magnetic storms that occurred on Earth were a consequence of this brightening that was seen at the sun, the flare. And as we've learned more about the sun, we've realized that it's the CME that actually causes the magnetic storm.
Roughly half the time a solar flare occurs, a CME follows. But it travels hundreds of times slower.
It is a massive coronal material that's coming off the sun, and that travels with the solar wind that streams continuously away from the sun at about 1 million miles an hour. So it takes about 93 hours for it to get to Earth.
On March 9th, a solar flare kicks up a wave of radiation from the sun. The wave travels at the speed of light across space. It hits the Earth's atmosphere in just 8 minutes. The coronal mass ejection arrives 4 days later. This is what causes the blackout. Unlike a solar flare, a CME isn't a spray of radiation. It's a barrage.
And all of a sudden, this big addition of 100,000 times as much energy is thrown at the Earth.
The CME creates immense electrical currents in the ionosphere. The upper atmosphere practically crackles with energy. The auroras light up the sky as far south as Texas. Rivers of charged particles flow through the atmosphere and induce powerful electrical fields 60 miles below at the Earth's surface. Suddenly, with no warning, a vast current jumps onto the power grid. The surge races through the system, and the network overloads. By scanning ice cores, scientists travel back to an age when a massive solar storm struck Earth. A huge peak in nitrate reveals a solar storm that makes the Quebec event look like a firecracker.
The most intense abundance change that we see in the ice core data occurred in September 1859. It was so intense that we call it a superstorm event. It knocked out telegraph service in North America and most of Europe, and it was also seen all the way down in Calcutta, India at the time. It was a major worldwide event seen just about everywhere.
Space scientist Gibor Basri wants to know why young stars create such huge flares.
If you take a given kind of star, say a star like the Sun, there's a direct correlation between how much magnetic activity you see on that star and how fast you spin it. The slower the star spins, the less activity it has on it.
The faster a star spins, the bigger the arcs, and the stronger the flares. The only way to protect our electricity network is to shut it down before the storm strikes. But how do you predict a solar tantrum? In December 2006, Hinodi captures this groundbreaking footage. A magnetic arc snaps, and a huge flare erupts.
What drives these large solar flares is the magnetic field, and specifically its electrical currents running through the magnetic field. So each one of these strands is essentially an electrical current prefabricated in the interior of the Sun, breaking through the surface and becoming visible, and then ready to power a flare.
Where the magnetic fields intertwine the closest, the currents are strongest. Sunspots. Sunspots form because the Sun's atmosphere is hotter than its surface. The magnetic arcs block the atmosphere, making the sunspots burn cooler than the surrounding surface. 6,300 degrees versus 10,000 degrees. Sunspots come and go in an 11-year cycle of maximums and minimums. Solar minimum has few sunspots and the fewest flares. At solar maximum, 200 sunspots or more, all firing magnetic arcs. A week before the Quebec blackout, astronomers identify a group of sunspots on the eastern edge of the Sun's surface. The blackout occurs during a solar maximum. The next maximum is around the corner, in 2012.